Okay, um, so I guess I'm recording this for you guys. So we finished off chapter 2, where we sort of introduced topology, and so now on chapter 3, we're looking at the concepts of connectedness and compactness. So we're going to have to just backtrack a little bit just to recall some set theory. So we need some background. So to illustrate what we want to talk about, let's have a look at this theorem about infinite sets. So if you've got a set, the following statements are equivalent statements to define a set as being infinite. There exists an injective function from the positive integers to our set. There's a bijection of A with a proper subset of itself, and the fact that A is infinite. Okay, so so 1 implying 2 is not so hard. So how can we get from an injective function from positive integers to a set to a bijection of A with a proper subset of itself? Well, the idea there here is that the positive integers, it's easy to come up with a bijection with the positive integers with a proper subset of itself. So just pick your favorite one. So here I just had just adding 1. So you send 1 to 2, 2 to 3, 3 to 4, etc. Another one is you could send n to 2n, whatever. So you have this. So in this case, because we're dealing with the map that sends a integer to its successor, then we can get a bijection from our set A to A, remove the singleton, which is the first element, which is given by f, subtract the f of 1, which is the first element, corresponds to 1 in the set A. Okay, so you just let G of the first element be f of the second element. Of the second element, f of the third element, etc. And then there'll just be the identity otherwise. And then we see that this is a bijection onto this proper subset of itself, right? Because G is an injection. So it covers all from Z, it will cover the entire image of F, just missing that one element. And it works. Okay, the fact that 2 implies 3 comes from what we did in section 6, which said that a finite set can have no bijection with a proper subset of itself. So the contrapositive of that says that if there does exist a bijection of A with a proper subset of itself, then A is infinite. And so the really interesting implication to finish off this theorem is that 3 implies 1. So that if A is infinite, we want to have an injective function which goes from the positive integers to A. Okay, so let's so assume that you've seen axiom of choice before. So let's do a proof without the axiom of choice. So we use some kind of induction, right? So since A is infinite, in particular, it's not empty, so we can choose an element, and we let that be f of 1. And then assuming that we have defined f of 1, f of 2, all the way through fn minus 1, then since A minus that F1 through Fn minus 1 is not empty, right? Because A is infinite. So therefore, if we take a finite set from it, it's still going to be infinite. So we can choose an element. So we choose that to be our F of n. Okay. So what's the problems with this? Okay, now recall back in when we did section 7, we proved a lemma, which was that lemma 7.2, that if we had an infinite subset of positive integers, then that subset has to be countably infinite. And so just let me remind you what we did there. Okay. Okay, so when we did lemma 7.2, we constructed this function h, where h of 1 was the smallest element of our subset C, and then we define h of I to be the smallest element of C, and then we took out h of 1 to h of I minus 1. Okay, so let's compare it to now. We're doing for 9.1, we're wanting f of 1 to be an arbitrary element of A, and then f of I to be an arbitrary element of A. So at first glance, it seems like we're doing the same thing. But it seems that the axioms of set theory don't allow us, because how can we define subsets? So what we want, usually how we define subsets is some property. So in the 7.2 here, we're defining things through the fact that we're looking at the smallest element. So it's some definite properties. Like we think of the subset of positive things, the subset of perfect squares, that kind of stuff. Other things we can do is, we can, given subsets, we can create new subsets by taking unions and intersections and complements. One thing that's perfectly fine is another way to create new sets would be, given a set, look at the power set of that, the set of all subsets of that. And of course, another way that a legitimate way of creating new sets is by taking Cartesian products of old sets. But here we have a little bit of trouble because how is F defined? The fact that it's arbitrary, are we allowed to do that? Are we allowed to construct a set using that? And so in some sense, F is so fuzzy. Whatever. So what happened was that around the end of the 19th century, people were starting to look at set theory and putting it on a firm logical basis. And they came up with this new axiom, a new way of being able to construct sets. So the axiom of choice says that kind of what we did before with F is legitimate now. Given a collection of disjoint non-empty sets, there exists a set C consisting of exactly one element of our collection. That is, a set C, that C is contained in the union of elements of A, and for each A in A, the set C intersected A contains a single element. So we're allowed to make it, we have this ability to choose. Okay. And so this won't help. This is not exactly applicable to our previous thing here. The proof that we want to make, because we haven't got a collection of disjoint non-empty sets. So this lemma here, which follows from the axiom of choice, is the existence of a choice function. So given a collection of non-empty sets, and now we have not necessarily disjoint, there exists a choice function, which goes from that collection to the union of the elements of B, okay? Such that we take a set, C of B is an element of B for every element of our collection B. Okay, so why does that follow from the axiom of choice? Okay. So the typical way that you use the axiom of choice is you want a collection of all non-empty subsets of a set. Okay, and so, of course, that's not going to be disjoint because you've got a singleton. You've got a set of singletons, subsets of singletons, subset of doubletons, which are going to include those singletons. Right. So what we're going to do is construct a disjoint collection from our arbitrary collection. Okay. So if we have, say, some element from our collection of subsets, let's have a look at the collection of ordered pairs B and an element of B. Okay, so I think I already have this down. Right. Yes, here is the proof. Right. So given an element of our collection, let B prime then be an ordered pair Bx, where B is our chosen element from the collection, and X is an element of B, right? So this is some subset of collection across all the possible elements that we can have. Okay. Firstly, B prime is non-empty, right? Because B is non-empty. Okay, so there does have to exist some X in B. Now, I claim that that if B1 doesn't equal B2, then the intersection between B1 prime and B2 prime is disjoint. Okay, now why is that? Okay, so if we have B1 not equal to B2, then the intersection of that is non-empty. Okay. Well, what is B1? Something B1 looks something like B1 X1, right? So, and this guy here looks something like B2 X2. So it's perfectly possible for X1 to equal X2 and B1 and B2 not to be disjoint. But as a Cartesian product, these things are disjoint, right? Because they are different in the first coordinate. So they're different in this product space. So let's just form the collection then of all these possible B primes. And this is a collection of disjoint non-empty subsets. So that means we can use the axiom of choice on C. So what we have by the axiom of choice, we have a set C consisting of exactly one element from each element of our collection C. So C looks like, write a little bit more of this. So C contains just one element, which is like Bx, whose first element. So there's only one element in C whose first coordinate is B. And so we let then C of B equal X. This is our choice function. Okay. And so now we can actually do our proof properly. So a more precise proof of the theorem, so we can use the axiom of choice. So recall, we're given an infinite set A, we wanted to construct a function from the positive integers to A. Okay, so we let our collection be the collection of non-empty subsets of A. Okay, that's good. So then we can apply the lemma to that. And so we have a choice function then that goes from this collection to the union of elements of B. But of course, these is this collection of the subsets of A. So the union of all the possible subsets of A is just A itself. So we get a choice function from the collection of non-empty subsets of A to A. So we have C of B, the choice function acting on a subset, is an actual element of B itself. And so now our recursion has no problem. So now we can define our function f by f of 1 is just using the choice function on A. This is now, it seems kind of flimsy, but it's now concrete. We have like a definite property we can use to define f. And then by recursion, we go through and f of n is in the choice function on A, subtracted all the first n minus 1 elements that we've chosen before. And we do that for all n greater than 1. Okay, and of course, you need A to be infinite to be able to do this recursion, because if A is infinite, at each step, when we take away an element, we're still left with an infinite set. So we can keep on choosing. F is now unique. It's based on C and our choices, and the fact that the F is injective also follows straight away. Okay, so when we have choice, axiom of choice, it seems pretty straightforward now, but at the time, actually, it was pretty controversial because, well, we're going to see in a moment that it actually has some interesting consequences. So we're going to have a look at well ordering. And so some of the things that are counterintuitive. So people have no problems with choosing from a finite or a countable set. It's when you get to uncountable sets that you can get some interesting paradoxical looking results. We're really not going to worry about those results. We're just going to use the axiom of choice whenever we need it. Although we're really not going to use a lot of the full power of the axiom of choice. We're just going to use it for a few examples. All right. But anyway, let's talk about well-ordered sets. So back in foundations, you would have done some stuff on order relations. The main thing I want you to recall from there is the idea of an order type. So if you have two sets with each having their own sort of order relation, then they're kind of isomorphic if they have the same order type. So that means there's a bijection from one set to another that that preserves order, i.e., so if F is our bijection, so if A1 is less than A2 in A, then F of A1 is going to be less than F of A2B. Move this with the bijection. Okay, so order type. So we'll talk a little bit about that more. So we say that a set is hello. We'll just pause this for a moment there. Hello. Recording. Okay. So a set is well ordered if every non-empty subset of A has the smallest element. So was this talked about in foundations? Okay. So how can we get well-ordered set example? Well, if you have a well-ordered set, then any subset of that is going to be well-ordered. Okay, because any subset of the subset is going to be a subset of the original set. So all the typical examples that we know of, like the positive integers under the normal thing is like the gold-plated example of a well-ordered set. And if you have any two well-ordered sets, then you can put the Cartesian product in the dictionary order. And that's pretty straightforward to prove, right? Because if X is some subset of A cross B, then you look at the set Y of first coordinates of X, right? And that's going to be some subset of A. So therefore, it has a small element. Let's call that A0. And then you look at the set Z equals B in B such that A naught B is in X. And that's a subset of B. And so it has a smallest element, say B naught, and A naught, B naught is your smallest element. So that's very straightforward. The integers, Z is not well ordered in the usual order. Because, for example, take this subset of negative integers, there's no smallest element. The unit interval, closed unit interval 0, 1 is not well ordered in the usual order. Just take the open interval 0, 1. That doesn't have a smallest element. Now, it's fairly easy to put a new order on Z to make that well ordered. You just do the negative integers first and the positive integers, whatever, or something. No one's ever been able to come up with a well ordering for that. Okay. Finite sets. Basically, for each n, there's only one ordered set of that cardinality. And it's the same as the order type of just a section of that. And the proof of that is pretty straightforward. If I give you a finite ordered set, since it's finite, it has the largest element, it's got a maximum. And why is there then, we want to then come up with the order preserving bijection of A with a section of the positive integers. Well, you just use induction, right? So if A has only one element, we're done. Okay, assume that it's true for up to n subsets of n minus 1. Then if you take your A, you just remove the largest element. You can put it, or by the induction hypothesis, you can put an order relationship on those first n minus 1 elements. Let's call that F prime. Then F is just going to be F prime on the non-maximal elements, and F of the F maximal element is going to be n. So very easy to construct a true proof of that. Countable sets, you can come up with lots and lots of different order types. So the usual one, that order type is called omega. But you can have omega plus 5, where we put the first 5 elements at the end, and now this is our order relationship. So we have a maximal. So this is different from this, right? We can tell this because this set has a maximal element, and this doesn't. It has a second maximal. Second, third, fourth, fifth, right? Or you can put you can put even numbers first and then odd numbers. This is basically the way that you would put an order on Z. So Z can be given this kind of order type. This is order type omega plus omega. Okay, so omega is an order type. We might call it an ordinal. All right. So that's the order type, the typical order type for countable infinity. So you know about Aleph null? So Aleph null is the cardinality of Z plus. This is the ordinality of usual Z plus. Okay. What's Aleph null plus 1 equal to? Aleph null. What about omega plus 1? Is that equal? That's not equal to omega. But 1 plus omega does equal omega. Right? Because what do I mean by 1 plus omega? It just means I add in a new minimum. Well, the integers or the positive integers already had a minimum. I just added a new one in, so it's got the same order type. In fact, you can do all kinds of interesting things, like 1 plus omega equals 1 plus omega equals omega plus 1 plus omega does not equal omega plus omega plus 1. So it's a weird thing. When we have R2, what is this 2? It's not a cardinal number, right? 2 is a typically you think this is a cardinal number. It's R2 because we've got 2 copies of R. No, it's an ordinal number. It means we've got a first thing and a second thing, right? Because that's what makes a Cartesian product work. You have a definite first thing and a second. So that 2, because there's only one finite ordinal, right? So 2 can represent both the cardinal number and the ordinal number. But with infinite, you've got trouble. So the cardinal numbers can't represent the ordinal numbers because of these kind of things. This is the kind of thing you can do in set theory. What about uncountable sets? So no one has ever been able to come up with a well-ordering of Z plus. And so now you know what that omega means. It means it belongs to this order type, right? So we can have Z plus omega plus 1, where we add in a maximal, something at the end. So that's beside the point. So you might think, well, can't we use the dictionary order? Because the proof that we gave before about A cross B, wouldn't that work? That only works for countable. That only works for finite products. So, for example, let X be the set of elements of Z plus omega, such that all coordinates are 1 except for 1, which is 2. Okay, you've got 2, 1, 1, 2, etc. In the dictionary order, there is no smallest element, right? Because you want to put the 2 right at the end. That would work in Z plus omega plus 1, because then we do have something to get to the end. But then we'd come up with other sets that would be wrong too. Okay. Now, notwithstanding that, Zermelo in 1904 came up with the well-ordering theorem, which says that any set that exists in order relation that is a well-ordering. And this kind of freaked people out when they saw it. And so in a course in logic or set theory, a standard thing to do would be to prove that this is equivalent to the axiom of choice. So the well-ordering theorem, the fact that the well-ordering theorem implies the axiom of choice is easy, right? Because for any set, just choose the smallest element. So that gives you a choice function for free. Going the other way is not super difficult, but it's long and belongs in a logic class. We won't do that. Okay, so really, the only thing in the well-ordering theorem that we'll use is the corollary, the fact that there is an uncountable well-ordered set. Even though no one has ever found one, there exists one. So like in the early 20th century, this really freaked people out. And so there was a school of mathematics called constructivists, which basically said that to do anything, you actually have to be able to construct things solidly. You can't have these waffly existence with like there exists. So they would never accept this as a theorem. You have to actually construct it yourself. But as I say, we're going to accept this with no problems whatsoever. Okay, so I don't think we have enough time, but I want to finish up by starting to construct a set that's going to be useful for us. And that's, let's return to the idea of section. So we've already seen sections for the positive integers, right? So the section of z plus by n is just a set of positive integers which are less than n. So we can generalize that to any set, to any well-ordered set. So given a well-ordered set, so that means not only do we have a set, but we have an ordering. Given an element of that set, then we're going to let S alpha be the section of X by that alpha, and that's just the elements of X which are less than alpha. So the main thing to remember is a section does not include that final element. And it's a very good reason why that's going to be. Let's see. So this is what we want. We want this S omega. There exists a well-ordered set A having the largest element omega such that the section of A by omega is uncountable, but every other section is countable. Which is, to stop and think about how weird that is. Well, this is what we're going to prove. So you're going to have you have your well-ordered set. It's up omega, and that's uncountable. This is uncountable. This is why you can't include omega. But if we choose any other place before omega, it's now countable. So this is perverse. This is kind of why people didn't like axiom of choice, because you can come up with this. But this is going to turn out to be important for us. So this is where we'll take up on Wednesday.